This is the second lecture of our course. Today we will talk about data structures. So our course is about algorithms and data structures. Last time we talked about algorithms. Today we'll talk about data structures. So, what is a data structure? Data structure, according to its name, data structure is some structure that contains some data. So we have some, I don't know, something like this, some structure, something, I don't know, something like that. And this structure contains some good data. Some data here. This structure may be very different from one data structure to another structure, so they all are very different, and what is a common thing that is some structured and it contains some data. Why do you need some structure for your data? Why can't you just get all your data and put it in some big array? Like create a big array and just encode your data in some form and just put it in the big array. Why you may need some structure? That's basically because you want to access your data. So you want to perform some operations. Operations. For example, if you want to build some database, you may want to find some element in the database by your request. Or if you create some, I don't know, some application and you want to show to your user some statistics, like show me the average income for the last year. So you want to be able to get these statistics fast. So you want to just look in your data structure and find these statistics. So these operations may be very different. And actually, these operations define what data structure do you need. So before you want to choose what data structure do you need in your algorithm, you want to decide which operations do you need. So first you decide what operations do you need, then you decide what data structure do you need. No, not the opposite. And all data structures are like divided in some classes. And each class is specified by the operations that are possible to make in the data structures of this class. For example, let's say very simple. Let's say array. Array is a very simple data structure. It's not exactly data structure, but let's say it's a data structure. Let's say array. Array. What operations can you do in array? In array, you can like put element in some by index. So you have index I. You can put element by the index and you can get element by index. Let's say get element by index I and put element. Let's say value v. So this operation is simply return AI. This operation is AI equal to. So it's a very simple data structure. It's actually not exactly data structure, it's more like a primitive, but good enough. Now, when you want to create a data structure, you specify the operations you need in your data structure. And when you analyze your data structure, you want to analyze the time complexity of each operation. So for each operation separately, we will calculate the time complexity. For example, in this case, we have two operations, get element and put element. And each operation actually is performed in constant time. So for both this operation, the time complexity is big O of 1. That's all. That's the first data structure we showed. Now, data structures and algorithms are strongly related to each other. Because when you create a data structure, you want to make operations, and when you make operation, you use some algorithm to make this fast operation. And when you design the algorithm, you may use some data structure just to make your algorithm faster. So algorithm data structure, we will learn them in parallel because they're very closely related to each other. Good. And today we will learn our first data structure. Our first data structure will be a binary heap. Good. So what is a binary heap? So heaps, let's say heap, or sometimes called it's how it's called. It has a second name. Is a priority queue. So heaps or priority queues are the class of data structures that can perform the following operations. So it contains some set of elements and you can do two operations, sometimes 3 or 4, but today we'll learn only 2 operations just for simplicity. Sometimes you can make some additional operations. We'll learn 2 operations. First operation is insert an element. And the second operation will be remove the minimal element from the heap. So remove minimal element. Minimal element means that you can compare to elements. So you have some comparator that can compare to elements, and there is always one element which is minimal in this set. Okay, so I want to make these 2 operations. Any questions by now? No. Good. Now, first, before we will learn how to make a right binary heap, we will learn how to make like simple data structures which can do these 2 operations. First attempt will be to use the simple array. So first attempt. Let's use just the simple array. And say, let's say that this array is big enough, so we always have enough room to put all elements of our set in this array. So we use first, let's say first n elements of this array to contain these elements of the set. So these first n elements from 0 to n minus 1 contain the elements of this set. Now let's just implement these 2 operations. So first operation is insert an element. So we need to insert a new element into our array. Easiest way to do this is just insert it in the last position. So we will get this element x, put it in the last position here, and increment the size of array. So we'll say insert x like this, and put it into position n, and then increment the size of array. Cool. Now the second operation. Second operation, we need to remove the minimal element. To remove the minimal element from array, we need to find this minimal element first. So how to find the minimal element in the array? So I hope you know how to do it. So to find the minimal element, let's just iterate over all elements and find the minimal one. So let's say j is the index of the minimal element. So first j equal to 0, then we iterate over all elements from 1 to n minus 1 and see if this element is less than this element, then update the minimal. It looks fine. So now we found the minimal element in the array. So let's say it's somewhere here. Just somewhere here is the minimal element of the array. Now we need to remove this element from the array. And when we remove this element, there will be a hole here. So we want always to keep all elements close to each other. So if we just remove this element, there will be some empty space here. To fill this empty space, we can, for example, swap this element with the last one. So we'll swap element j with the last element of the array, and then remove the last element from the array. Let's say swap a j with a n minus 1. And then just remove the last element. Let's say n minus, and then return is correct. Looks fine. So we found that first the minimal element, then swap the minimal element with the last element. Now the last element is the minimal one, so we decrease n and return this last removed element. Good? You can say something in the chat from time to time just to keep it live. Okay. So this is the first simple implementation of the heap data structure. So it is a correct heap data structure. We can insert elements, we can remove the minimal element. Now, let's calculate the time complexity of this data structure. In this data structure, time complexity is different for these operations. So this operation costs you constant time. Why we return a n? Because we decreased n. So let me show here. So we had array A. Here we have element j, and we had elements from 0 to n minus 1. So this was the minimal element. Now we swapped this element with the last one. So we swapped these two elements. So now we have elements from 0 to n minus 1, and this is the minimal element. Now we decrease n, so we have this array, and minimal element is here. So in the end we want to return this minimal element, so minimal element has index n. No. This needs to be a compromise between spamming in the chat and be quiet too much. So just don't spam, but not to be very quiet. There's not so many of you, so I hope it will be fine. Cool. Now, what is time complexity of this operation? In this operation, you need to make this this for loop, and this for loop iterates over all elements of the array. So the time complexity of this part of this operation is linear. So the total time complexity of this operation will be big O of n. So this is the example of data structure where we have two operations and they have different complexity. So this operation have time complexity big O of 1, and this operation have time complexity big O of n. Sometimes it happens. Okay, let's try another one. So if we want to perform this operation fast, so if we want to remove the minimal element faster than just in linear time, what can we do? For example, we can maintain the sorted order in our array. So if you keep the array sorted, then it's easier to find the minimal element, because minimal element will be always in the end of the array. Let's try. So second attempt will be to have not just array, but a sorted array. Cool. So if we want to be able to remove the minimal, it's better to have sorted array in descending order. So we will have array A sorted in decreasing order. So the minimal element will be the last one, from 0 to n minus 1. So minimal element will be always here. Now it's easier to make this remove min, because we can just skip this part. Minimal element is always in the end, so we just decrease n and return n. No, when I decrease n, no, the minimal element has index n minus 1. So after I decrease n, the minimal element will have index n. I have indices from 0 to n minus 1. So it was n minus 1, then I decrease n, now it is index n. Good. So we can easily remove the minimal element from the heap. And now we need to be able to insert new element. And this is complicated because we need to keep the array sorted. So when we add element x here, we need to put it in the correct position. So we need to put it in such position that the array remains sorted. No, let's say easiest way to do it is like we did in the previous lecture, like when we had insertion sort. We'll put it here and then move it to the left until it reaches the correct position. Let's say, so we put it in the last position and then move it to the left. So let's say I equal to n minus 1. So I is the index of element x, and now while I is greater than 0 and it is greater than the previous element, I just swap them. And decrease I. Again, this procedure is the same as we used in the previous lecture when we had insertion sort. We put the new element and then move it to the left until we had element that is greater than this element. So after this while, this array will remain sorted. Good. So what is time complexity? Here the time complexity of remove min is obviously constant. But now the time complexity of this insertion is big, because here you need to make this while, and the time complexity of this while is again linear, so this time complexity is linear. Okay, now we have two options. We can make fast insertion but slow remove, or we can make fast remove but slow insertion. In the real algorithm, you can choose between these two structures, but actually they are both pretty slow, because in the real algorithm you have big number of insertions and big number of removals. So the total time complexity of the algorithm, if you use this data structure, will be slow. So now we will implement the first version, no, the correct version, the correct binary heap. And in the correct binary heap, we'll have both these time complexities less than big O of n. And actually, the time complexity will be big O of logarithm of n. So, show it here. So we have two versions. Let's see. We have insert and remove min. First version, this one. We have insertion in constant time. This is n. Second version is n here and 1 here. And now we'll make the correct binary heap. In correct binary heap, we have both this operation working in logarithm time. So we have first version. This spoiler, we will discuss it now. So both this operation will have log n time. It's hard to compare two data structures. So, for example, if you compare these two data structures, so this operation is faster, but this operation is slower. That's usually what happens when you compare to this structure. But when you decide what data structure you can use in your algorithm, you need to calculate the number of operations you need to have. For example, if you want to make an operation, let's say we have some algorithm and we need to perform like n insertions and n removals. Then what will be the time complexity? So in this case, we have n insertions, it costs you n time. And then you have n removals, each costs you n time, so total time complexity will be n plus n squared. And here you have n insertions, so we have n squared here plus n. And here you have n log n plus n log n. And now you see that this data structure is better than this data structure, because here you have n log n time complexity, and here you have n squared time complexity. So if you have this number of operations, you can compare and see which data structure is better. Usually you have like a situation like this. So this is the common situation. Usually you have about equal number of insertions and removals. So that's usually what happens. So usually this data structure is better than this two. Because when you insert element in the heap, usually you need to remove it at some point. So usually you have the same number of insertions and removals. So, okay. No questions by now? Okay. Let's go. So now we'll discuss the binary heap. The binary heap looks like this. You have a binary tree. How many elements? It's enough. Let's go one more. Sorry. Good enough. You have a binary tree. What is a binary tree? It is the set of nodes. So each node have at most 2 children nodes. So we have one child is left child and another child is right child. And this binary tree for the binary heap will always look like this. It will be almost complete. So all layers of the binary tree will be full except maybe the last layer. In the last layer you have some elements from the left, but maybe not all elements to the right. Just because you don't have enough elements in your heap. So, for example, if you have 1, 2, 3, let's say, if you have 10 elements in your heap, the binary tree will always look like this. So the structure of binary tree is fixed by this number n. If you have 10 elements, you will always have binary tree like this. Now, each node of this tree contains one element of the set. So if you have 10 elements in the set, you have this tree, and each node contains one element. It's maybe hard if you don't know how to program. So if you are new to programming, maybe first thing you need to do is to learn some programming language and just learn how to get simple algorithms, like, and learn how to solve some simple problems. Go. So now each node of the tree should contain one element of the set. And we want to be able to find the minimum. So to be able to find the minimum, we will keep this tree in some almost sorted order. This is called the heap property. So the property of the heap is that each element is less or equal than its children elements. So this element is less than this element, and this element, and this element, and this element, and this, and this, and this. Which programming language should I begin with? It doesn't matter actually. You can choose any programming language and just start to learn it. It's more than enough information in the internet how to learn programming languages. Go. So now we want to put our elements in this tree so that for each pair of nodes, these elements will be less or equal than this element. For example, let's put some elements here. Let's say we have 2, 5, 10, I don't know, 7, 9, 13, 8, 26, and 15 here, and 19 here. So this is the correct binary heap. We have all 10 elements in these nodes of the binary tree, and for each node it is greater or equal than the parent node. Nice. Okay. Now, how can we store this element in our programming language? There are different ways to store the binary tree in the programming language. Usually when you have binary tree, you have something like this. You have like class node, and you have like pointers to the left child and to the right child. You have some complicated data structure. But in our case, this structure of the tree is fixed. So the tree of size 10 is always look like this. So we don't need to just remember which element is the sum of which element, because we always have this tree looks like this. So instead of having some complicated structure of nodes, we will just enumerate all the nodes in the right order. So we'll enumerate all the nodes from top to bottom, from left to right. So this node will have index 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And now we'll just simply create an array of size 10 and put these elements in this array using these indices. So let's have this array, and we have elements 2, 5, 10, 7, 13, 15, 19, 9, 6, 26. 2, 9, and 10 switch. No, it doesn't matter. So we only need the relation between element and its parent. So these two elements have no relation, so they may be in any order. And like any other, so this element and this element may go in different order, and so on. So we only need to maintain the relation between the element and its parent. Sorry. Okay. Now to store this tree in the programming language, we'll have this one array. Let's call it array H from the heap. And to access the element of the tree, we just get its index. So for example, we want to access this element. It has index 4. So we go into this array, find the fourth element. So this will be. This is element of index 4. We just take this index, go to array, find the element of this index, and this is the element of this node. Good. Now, we will need to traverse this tree. So we need to move to the parent or move to the child nodes. So how can we move around the tree using this array? That's quite simple. So, for example, if we stay in some node, so we stay in some node I, and we want to move to the left child of this node, to this node. We don't have the link, so we don't have the pointer from this node to this node. So instead of having pointers, we just calculate the index of this node. If we stay in node I, the index of the left child will always be equal to 2i plus 1. And the index of the right child will always be equal to 2i plus 2. You can prove it using mathematical induction. I will not do it, but if you want, just for the exercise, you can try to prove it that for any node I, the left child always have index 2i plus 1, and the right child will always have index 2i plus 2. This is true because the tree is complete, because all layers of the tree are complete from left to right. So you have 2 in power of I elements on the layer I. So this one. For example, if you stay in node, let's say you stay in node 1. So you stay in here. This is I. And you want to move from this node to this node. So you only know the index of the node. So you know the index is 1. So you stay here. And you want to move to the left node of this element. So you calculate 2i plus 1. It will be 2 multiplied by 1 plus 1. It will be 3. So you know that the index of the left child is 3. So you move from this node to this node. And this node will be the left child of this node. Good. And sometimes we want to move to the parent node. So let's see. What is the index of the parent node of the node I? Basically, if it is a left node, we need to calculate I minus 1 divided by 2. And if it is right node, it is I minus 2 divided by 2. It can be simplified like this. We'll say that the index of the parent is I minus 1 divided by 2 and rounded down. So if it is even, then we'll have rounded down to 2i. If it is odd, again, we'll have I minus 2 divided by 2 will be equal to I. So from here, you will have I plus 0.5, so it will round it down to I. From here, you will have I, so it will be rounded down to I. So this is the correct formula for both cases. Okay, any more questions by now? Don't see any questions. Okay. I think that's all preparations. Now we're ready to make operations. First, let's learn how to insert elements. So when you need to insert new element in the binary heap. Remove this. Let's say you insert some new element. It's floor, so it's rounded down. Cool. So let's say you want to insert new element in the binary heap. Let's say you insert new element. What is this? Let's say insert 4. So we want to insert new element 4 in binary heap. So what is the easiest place to insert new node in the binary tree? To insert new element in the binary tree, the easiest way to do is insert it here. So we'll create a new node in the last layer, which is not full, in the leftmost position. So we'll insert it here. Put it here. So it has index 10. Now we have a good binary tree. So again, we have all layers full except the last layer. Last layer have some full elements from left and some empty elements to right. And now we just need to maintain this property, because this property that each element is greater or equal than its parent is broken here. So for this element, we have element which is less than its parent. So here is the problem, and we need to fix it. Well, let me just write the code here. So let's say we have insert x. So first we put element in the last position. Last position has index n. So again we'll say h n equal to x n plus plus. Yeah. H. This is n. This is h. This is h. This is n. Now we put this element here, and now we need to fix this broken property, because for these two elements we have lower elements less than its parent. How can we fix this property? Very easily. We just will swap these two elements, and if we swap these two elements, when we move this 13 down, move 4 up here. Now what happens? This property is satisfied because we have big element here, now we have smaller element here, so this property is still satisfied. This property now is satisfied because we moved the smaller element up, so this property now is satisfied. Here we have a lesser. So now the only broken property may be in this node. So for these two nodes, we may have the broken property of the heap. So now we have this element less than this element. So this is the only place in the heap where we can have a problem. All other edges are satisfied. Cool. Now again, we need to fix the property for these two elements. Again, we'll just swap these two elements. So 5 goes down, this 4 goes up. Now we have this property satisfied, this property satisfied, the only property that may break is for these two nodes. So this is the only place where we can have a broken property. We check the property for these two nodes, see that this node is greater or equal than its parent. So here is satisfied, here is satisfied, here is satisfied. So for all nodes, the property is satisfied. So we have the correct binary heap. That's all. That's how you insert new node in the binary heap. You insert in the last layer, and then move it up until you have the satisfied property for this element in its parent. So let's just write the code. Let's say again, I is the index of the element x. So first we put position n, increase n, I equal to n minus 1. So now I is the position of the element x, of the new added element in the binary heap. And now we just move it up. So while we can move it up, we can move it up if it is not the first element. So if I is greater than 0. And it is less than its parent. Less than its parent. And parent have index I minus 1 over 2. If it is less than the parent, then we swap these two elements. Swap AI and AI minus 1 over 2. And continue to the new position. So I equal to I minus 1 over 2. Yeah, that's all. Let's insert another element. So let's insert another element. For example, insert 2. We only have element 2. You may have equal elements. That's not a big problem. Let's insert one more element. So let's insert one more element. So new element must be the next element in the last layer. So next element will be the left child of this 15. So we insert new element here. It will be the left child of. It's not enough room here. So let's just move to left. 26. Okay. So let's insert more element here. So we insert new element like 2 here. Now look on this property. It's broken. So we swap these two elements. Move 15 down. Move 2 up. Now we say I. So I was here. Now we swap element I and element I minus 1 over 2. We swap these two elements and say I equal to I minus 1. So I moved here. Now again, we compare element I and its parent. This element is less than parent element. So again, we swap these two elements. M is here, 2 is here, and move I to the parent. So I now is here. And now again, we compare element I with this parent, see it is greater or equal, because they're equal. So this property is satisfied, everything is satisfied, so it's fine. Now again, we have the correct binary heap. So for any element, we see that it is greater or equal than its parent element. So we have a correct binary heap. Whew. That's all. Now, let's calculate time complexity of this algorithm. So what is time complexity? Time complexity will be equal to the number of iterations of this while loop. So we need to calculate the number of iterations here. Here on every iteration, we move to the next layer of the tree. So we start on the bottom layer of the tree, and then each time we move to the next layer of the tree. The number of layers of this tree will be equal to logarithm of n. So we have at most logarithm of n number of iterations here. So total time complexity of this function will be big O of log n. As expected. that's how you insert new element in binary heap in logarithmic time. And now we need to learn how to remove elements. Let me check if you have any questions. No, I don't see any questions. Good. Now let's see how to remove elements from the binary heap. First, again, we need to remove the minimal element from the binary heap. How to find the minimal element of the binary heap? That's quite easy, because for each element we know it is less or equal than its children. So the minimal element of the binary heap must be in the root. So minimal element is always here. So we don't need to spend any more additional time to find the minimal element. We always know that minimal element is in the root of the tree. And root of the tree have position 0 in the array. So just this first element of the array will always contain the minimal element of the binary heap. Good. So now we located the minimal element. It was easy. Now we need to remove this minimal element. That's a little bit more complicated. If you just remove the root element from the tree will break into two parts. It will have left subtree, right subtree, and we need somehow combine these two subtrees in one big tree. That's not easy thing to do. So instead of just removing this node tree, so we need to remove this node. So let's remove this. When you remove the root node, you have two independent subtrees, left subtree and right subtree. And to combine it in the one big tree, we'll do the following. We'll take the last element of the tree, this is 15, and put this 15 as new root of the tree. Just remove it from here and move it to the top. So this is new element. I just remove everything unnecessary. Just remove everything just to keep the picture simple. So we removed the minimal element, it was in the root of the tree, and replace it with last element. We take this last element from the bottom layer and put it in the place where the root was. Good. Now we have the correct binary tree. So we have all layers filled except the last layer and so on. And now instead, the only problem we have that we have this property of the heap is not satisfied. It is not satisfied for these two nodes. So here we have less and here we have less. So these two nodes are broken. So here, for these two nodes we have elements which is less than the parent element. Good. So how can we fix this property? To fix the property for both these nodes at the same time, we'll do the following. We'll take one of the children, actually the minimal of the children. So we look on both children, see which child is minimal one, and swap this root with the minimum of the children. So this 2 is less than 4, so we swap this 15 with this 2. So 15 goes here, 2 goes here, 15 is new, 15 goes right, and 15 goes here. So again, we had two children. One was 4, another was 2. And we need to satisfy these two nodes at the same time. To do this, we take the minimum of two children and swap our element with this minimum. Okay, now, these two properties are satisfied. So here we have less or equal, here we have less or equal. And now we may have these two properties broken. So now we have, for example, this property broken. These properties, now we have here less. No matter which element we put in the new root, as long as both of the right elements. Yes, but it is not matter which element move to the root, but it's easier to move the last element, because when you remove the last element, you have the correct binary tree. So if you move element from the middle of the tree, you have hole here, so it will be a not correct binary tree. So the easiest way to remove element from the tree is to keep it the correct balanced binary tree, like we want all layers to be filled except the last layer. So this element is just easier to remove. You can move any element to the root, but if you remove like this element, you have hole here. And we don't want to have any empty spaces in our binary tree. Yeah, but we can take any element and put it in the root. And now we have a problem here. We have this element less than this element. So again, if we have a problem like this, we just swap these two elements like we did before. So this thing goes here. This then goes here. So now this is satisfied, this is satisfied, now everything is satisfied, so we have the correct binary heap. Good. Not enough space on this board, so I need to erase this. Hope you don't have any questions. Hope you don't have questions, so I will just erase this. And this actually. Oh, sorry. Go. So let's write a code. I need to remove the minimal elements. First, again, we take the root elements, remove it, and replace it with the last element. How can we do it? Let's just simply swap these two elements. Let's just swap these two elements, like first element and the last element. It was not A, it was H. So just swap the first element with the last element, and now remove the last element. Like this. Okay, now we have this last element in the root of the tree, and we just move it down. That's a little bit more complicated than before, because in the previous operation, when insert element, we only swap the parent, and we have only one parent. When we look on the children, we may have 0 children, we may have 1 child, we may have 2 children. So the code will be a little bit more complicated, but I'll try to make it as simple as possible. Let's see. So I is the index of the new element. So again, like before, I is the index of the broken element. So this broken element may have incorrect property for these 2 children nodes. Let's see. So each time we will find the minimal of these 2 children and try to swap this minimal child. Sorting algorithm. We will build sorting algorithm, but later. We're talking about binary heaps by now. We will create a sorting algorithm. Let's go. So we will look on both children. Let's say, well, let's just see roll through. Now, let's see why I have at least one child. So let's move element down until I reach the bottom layer. So when I have at least one child, so if I have left child have index 2i plus 1, so while 2i plus 1 is less than n. Yeah. So it means I have at most one child, at least one child. Now, we need to take minimum of these two children. Let's say j is the minimum of two children. So we say j equal to 2i plus 1. If the right child is less than the left child, so if I have the right child, so if 2i plus 2 is less than n, and this child is less than this child, and not a but h, 2i plus 2 is less than hj, then just say j equal to j plus 2. So now j is the index of the minimum of two children. So this child or this child. So. Now let's see if this minimum is greater than the element I. It means that both children are greater or equal than the element I. It means that these both properties are satisfied. So if hj is greater or equal than hi, it means that both children are correct, so we just can return here. Let's break here. Break. We can just break from this cycle. And now, if it is less, then we make the swap. Then make swap hi then hj and say I equal to 0. Looks fine. Yeah. Yeah. This lecture is full of jokes about parents and children. Yeah. Cool. I think that's fine. So we find minimum of these two children. So we take the left child. If we have right child and right child is less than left child, then j equal to right child. Now j is the index of the minimal child. We just see if it is correct, we break. If it is not correct, we swap with the minimal child and then move to the minimal child. Looks fine. Now in the end, we need to return this removed minimal element. So in the end, we just return hn. Whew. Looks fine. While two, because we need to make this while only until we reach the bottom layer. So if 2i plus 1 greater or equal to n, it means the left child is outside of the tree. So we don't have the left child. If we don't have the left child, we don't have the right child, because right child have bigger index. So it means we have at least one child here. If we don't have any children, then all properties are satisfied. Because property is only broken when we have element I and its children. Yes, it is the index of the left child. If the left child is less than n, it means left child exists. We already discussed this. This tree represents the memory like in the big array. So we have index of each element from here. 1, 2, 3, and so on. and we just put these elements using these indices in array H. We have this array H contain all these elements using these indices. No, you don't use linked list here. So the linked list is not. In linked list, you can't access element by its index in one operation. So we use like normal arrays instead of not any lists or something. It's just arrays. Okay. Now let's calculate time complexity. Time complexity here will also be logarithmic because again, on each iteration of this cycle, we move one to the next layer of the tree. We have at most logarithmic number of layers, so the total time complexity here also will be logarithmic. Oh, that's basically all. Now we have both operations. We can insert elements in logarithmic time, and we can remove minimal elements in logarithmic time. Cool? Cool. Now what we will do, we will use this binary heap to create a sorting algorithm. Like I said in the beginning of the lecture, you can use data structure to make some fast algorithms. And now we'll make the sorting algorithm using this data structure. Let's go. So this sorting algorithm is just called heap sort, just because you sort array using heap. Heap sort. Let's see. We have a function sort which takes array A. So how can you sort array using binary heap? Actually, very easily. You take all elements of your array, insert them into the heap, and then remove elements from the heap one by one. So first you will remove the minimal element, then you remove the second minimal element, and so on. So you remove the elements of the array in increasing order. So we'll just put all elements in the binary heap. And then remove all elements from the binary heap. That's all. So when you have the correct data structure, some algorithms may be very simple. So just add all elements, then remove all elements. And in the end, you have the sorted array. Nice. What is the time complexity of this sorting algorithm? Well, it's quite easy to calculate. So each operation costs you log n time. We have n operation here, n operation here. So we have total 2 n operations. Each operation costs you log n time. So total time complexity will be n log n. So time complexity is the same as in the merge sort algorithm we discussed in the previous lecture. More questions? Now let's make some improvements. So this is the correct sorting algorithm. We can use it. Now let's try to improve it a little bit. The improvement will be the following. So let's try now. If we implement it like this, we need to have 2 arrays. So just erase that. So imagine you have some array. Yes, you can do the same using binary search tree. Yes, that's correct. But binary search tree is a little bit more complicated data structure. We'll discuss it in the next semester. Yes, you can do the same using any binary search tree. Yeah. Now, what's happening? We have array A, and we need another array H. if you want to sort the array of size n, you need to create another array of size n, just to put all to use it as binary heap. Now you take all elements of your array, move them to the binary heap, and when you move all elements binary heap, you need to move them back to array A. So you need to create another array of the same size. That may be too much, because sometimes you have not enough memory. Because sometimes, if your array is big and fills almost all your memory, you don't want to create another array. So how can we do heap sort without creating a new array of the same size? Let's see what's happening. So we have array A. I still need it. So what's happening? You have array A. You move from left to right and take elements from array A and insert them into array H. So you already inserted this element into array H, and now you have only these elements remaining. In array H, you have this only this part of array H is filled. So the number of elements in array H is the same as the number of elements you removed from array A. So here you have the. So that's what's happening. So you take one element from array A, insert it into array H, using binary heap algorithm. Now you take the next element, move it here, and so on. Okay. We'll add more cats in there. Now, how can we improve it? Let's see. We use only this part of array A and only this part of array H. Now let's combine these two parts into the same array. So instead of having two arrays, we will have only one array. The same array we take for the source. So we take this array A and use its left part as a binary heap. So we'll split it into two parts. Here we'll have a binary heap, and here we'll have the rest of the array. So now on each iteration, what happens? You need to take the next element from array A and insert it into binary heap. So how to insert new elements in binary heap? You put it in the last position of the binary heap and then move it up to the tree. It's called shift up operation. So when you have the element in the bottom layer and then move it up using the insertion procedure. So this operation called shift up in the binary heap, and this operation called shift down in the binary heap. So when you add this new element in the binary heap, you add it in the last position, in the last layer of the binary heap, and then shift it up to the root. So how can, if we use the single array, we just look on this element. We need to put it in this position of array H, but it's already in the correct position. So we just take this element from this position here. Imagine it is now in the binary heap, so we just increase the size of a binary heap to here and shift it up to the root of the binary tree. That's all. So in the end, you will have the whole array A as the array of the binary heap. That's right here. So we go from left to right, then take each element and shift it up to the root of the binary heap. So shift up. Right. Shift up is this part of the insert operation when you have while and move element up to the root. Now, in the end, you will have the whole array be the array of the binary heap. And now you need to remove elements. So when you remove the element from the binary heap, what happens? So let's show it in dynamic. So first you have array A. Now you add elements one by one. So you have heap here. And each time you add one more element to the binary heap and so on. So in the end, you will have whole array equal to binary heap. So whole array is a binary heap. And now you remove elements from the binary heap. So each time you remove element and put it in the end of the array. So, so first you remove the first element, put it in the last position. Then you remove the next element, put it here, remove the next element, and so on. So you remove elements in increasing order, so this element will be put here in some decreasing order, so something like this. Again, this is the first element removed, this is the second element removed, and so on. So in the end, you will have the array sorted in decreasing order. Then you can just reverse the array, or you can modify your binary heap to remove not the minimal element but the maximal element. If you want to sort array in increasing order, you can just remove not the minimal element but the maximal element. Well, let's go. So what we do? We just go from right to left. 2, 0. And say that I equal to remove min. I don't want to use just modify it. Just use sieve. I want to use only this part of the. Is this the sieve down procedure? Sieve down. So I'll just swap this element to the last element. So I take this element, swap of this element. This is the minimal element. I swap them, and then sieve down this element. Shift down. That's all. That's how you make the heap sort without creating an additional array. So you only use the array that is given you as array A. So you take this array A, make this array a array of the binary heap, and then remove these elements from the binary heaps and put it in the same array to create the sorted array. That's basically all. Any more questions by now? Miss the cats on whiteboard. Let's draw some cats. Okay. Nice. Yes, it may be a little bit more complicated, little bit too complicated if it's the first algorithm you learn, but I think it's quite clear by now. So now, the final thing I want to discuss is how to create a binary heap in linear time. So now And now, oh, that's strange. Okay, let's try one more time. Okay, take two. So what I want to do, I want to improve this part of the algorithm. I want to create the binary heap from the given elements in linear time. What happens now? Now we add elements to the binary heap one by one. So first we add this root element, when we add these two elements, and these four elements, and so on. How much time does it take to add element? It depends on the height of the tree. So this first element we can add in one iteration. So we just add this element and we don't sift it up because it is the root of the tree. So we spend like 0 time to sift this element. Now for these two elements, we may want to sift it up to the root. So for each of this element, we spend one operation to sift it up to the root. Now for these elements, we spend 2 operations. For these elements, we spend 3 operations. And so on. So if we have more layers, in the last layer we spend log n operations to sift it up to the root. So the total time complexity will be something like this. It will be the sum for all layers. Let's say we have k is the number of the layer from 0 to log n. And for layer k, we have 2 in power of k elements, and for each element we need to spend k operations to sift it up to the root, multiplied by k. This sum is big. Why this sum is big? Because basically because on the bottom layer of the tree we have big number of nodes, and for each node we need to spend log n operations to sift it up. So in the worst case, we have all elements, all small elements in the bottom of the tree, and we need like to sift all these elements in the bottom layer to the root, one by one. So each this sift up operation calls to log n time and have n over 2 elements in the bottom layer. So this is omega of n log n. How can we improve this part? This is quite simple. We will try to move elements not up to the tree, but down. So instead of sift up operation, we'll use sift down operation. How can we go from bottom to top? And each time we have something like this. So this bottom part is correct. So here we have all properties are satisfied. Now we take the next element. And try to satisfy these two properties. To do this, we make the same operation as when we remove the minimal element. So we make the sift down operation. We just sift this element down to the bottom of the tree. So this element will be, again, this will be correct. So after each iteration, we have this part, this bottom part of the tree, contain the correct part of the binary heap. What will be the difference? The difference will be the following. So now we have many elements in the bottom layer, but it's easier to sift down these elements because they are already in the bottom. So we have different situation here. So in the bottom layer, let's say we only have this number of layers. So for these elements, when you sift down them, you just spend 0 operations. For this element, you spend 1 operation. For this element, you spend 2 operations and 3, and so on. So for the root, you spend log n operations. Okay. So we will not sift elements up to the root, but down to the bottom. What will be the time complexity if we do it this way? Let's see. Time complexity will be, it will be the sum for k from 0 to log n. So again, in layer k, we have what is the easiest way to calculate this? Well, let's say it's 2 in the power k elements on layer k, and the number of operations is, well, let's say log n minus k. Yeah. Good. Now let's show this function is big of n. How to show this? Let's calculate this sum in a different way. Let's calculate for each layer the number of swaps we need to make to sift all elements from the bottom. So let's say if we have layer k, let's calculate the number of swaps you need to make to sift all elements from this layer down in the layer more than k. So each element from this top part will be sifted down to this part at most once. So for layer k, we need to make at most 2 in the power of k swaps. From layer k to k plus 1. We make no more than 2 in the power of k swaps. So the total number of swaps in all sift down operations will be the sum of k from 0 to log n to the power of k. And this sum is the sum of geometrical progression. So this sum equal to 2 in the power of k plus 1 minus 1. 2 in the power of, not k, not log n. Log n. 2 in the power of log n plus 1 minus 1. And this equal to 2 multiplied by n minus 1. This is big of n. Again, what is the idea? The idea is we have a big number of elements in the bottom of the tree and small number of elements in the top of the tree. So we try to make fast operations for this big number of nodes and some small operations for this top part of the tree. So we have big number of elements here, but they are fast to sift down, and we have slow sift down here, but there are small number of elements here. So the total time complexity will be linear. Okay, that's basically all I wanted to talk to today. Any more questions?